Hello, calculus. Sorry I cannot be there today, but we're going to go through some stuff anyway. So we're going to be talking about finding the area under a curve. Under a curve. Now I say curve, but when we talk about curves, that just means any function. Lines are technically curves, but the lines are really easy to find the area under. You could even just use geometry to do that, which is one way we're going to check our work. So we're going to start out with the infamous problem that I've been trying to complete this whole time, being the function that is 1/2 x plus 2. Sketching this, it's going to look something like that. And let's say we want to find the area under this from 0 to 6. So using geometry, it'd be fairly easy to see where it intersects the y-axis at 2. The area of this lower rectangle is 12. The area of the upper triangle is going to be 9. Feel free to check that on your own. So it's fairly easy to see that this area is going to be 21. But let's use some calculus to figure this out. So first thing is that if we want to use rectangles to find the area under this curve, we're going to need some number of them. I don't know how many we'll need, so let's just say n number of rectangles, and we're going to start our incrementing at 1. Now to find the area of a rectangle, it is the height of the rectangle, which is going to be whatever x increment we put into the function, and its width is going to be however many rectangles we have split among 0 to 6. So we need to kind of define this x sub I and delta x before we get started. So delta x, we can define that they're all going to be the same width. All the rectangles are going to be the same width. So we can define this as going from our endpoint to our starting point and dividing that by the number of rectangles we have. So we can actually maybe write this more algebraically as b minus a over n, where b is our endpoint and 0 or a is our starting point. And again, n is the number of rectangles we have. Now our x sub I is going to be our starting point plus something. Now we can call this something. Since we're starting at 0, that's going to be a little bit helpful. But let's say we were starting at 1, and let's actually go to a new page. Let's say we have some curve, doesn't matter what it looks like, and we're going from 1 to 3. Let's just go from 1 to 2 for now. So let's say we want to split this into 10 equal pieces, 10 equal rectangles, pretend those are equal. Well, where the width of the first one is 1 plus 1/10, and the second one is 1 plus 2/10, and then 1 plus 3/10, and then 1 plus 4/10, and 5/10, and ... So what we can say is that we're taking 1 plus our incrementer I over 10. And we use I over 10 because we are splitting it into 10 pieces. So if we want to write this more algebraically, we can say A plus I over n. Now this is great because we're splitting it, the width of the area that we're trying to find is 1. However, if it's something bigger, let's say we're splitting it between 1 and 3. So now our width is 2. So we actually have to multiply this, the numerator, by 2 because that is the width of our area. So maybe another way we could write this is that our x sub I will be A, our starting point, plus our delta x times I. So our delta x, for our scenario, our delta x was 6 over n. This time we want 6 over n times I. So this will be I delta x or x delta xi, doesn't matter how you write it. So we can rewrite this whole thing now as the sum from I equals 1 to n f of x sub I. What we're doing is we're putting x sub I into our function. And so in our case, x sub I is going to equal our starting point, which is 0, plus I times delta x. Well, let's see what delta x is. Delta x is going to be our endpoint 6 minus our starting point 0 divided by the number of rectangles. So delta x is 6 over n. So x sub I is going to be 6i over n. Okay, so 6i over n is going in for every x in the function. So we're going to have 1/2 x, so this is the 6i over n, plus 2, and all this gets multiplied by our delta x, which in our case is 6 over n. All right, well, that's the summation, but we didn't pick the number of rectangles yet, and that's for a very specific reason. That we've been talking about the more rectangles you have, the more exact the area under your curve is going to be. So what we can say is that maybe we want the number of rectangles to be as big as it possibly can. In that case, we would want an infinite number of rectangles. So the way we can do that is to take the limit as n is approaching infinity of this summation. My limits are going to get sloppier the further this lesson goes, so whenever that's squiggly in front of everything, that's the limit. All right, so right now we have just a bunch of algebra to break this into separate pieces so there's not parentheses everywhere. So we still have the limit as n is approaching infinity of the sum from I equals 1 to n. If we put if we combine the 1/2 and the 6i over n, we get 3i over n, 3i over n, plus 2. And this gets multiplied by 6 over n. So we need to multiply that by 6 over n. So now we're looking at the limit as n approaches infinity of the sum of I equals 1 to n. When we distribute the 6, we get 18i over n squared plus 12 over n. And now we have some things that we can use the summation properties on. So we were talking about this a couple classes ago, that this, first of all, in this first term, this one right here, keep forgetting you can't see me point, we're going to look at this as the sum from I equals 1 to n, but this 18 over n squared, that's actually going to be a constant, so we can pull that out front. And now we're only taking the sum of I. And the second sum from I equals 1 to n, not infinity yet, of 12 over n, well, that's also a constant. So using the properties that we've been talking about, this would be, the first one is going to be 18 over n squared. The rule for summing just I is n times n plus 1 over 2. And the rule for summing constants is just the constant times n. There's first lunch. And we can simplify this a bit. These n's cancel out. This n cancels with one of those. So we're left with the limit as n approaches infinity of 18. Actually, that 18 and 2 can cancel, and we'll be left with 9 times n plus 1 over n plus 12. If we want this to be common denominators and distributing the 9, this would become 9n plus 9 over n. And if we put 12 to have a common denominator, it would be plus 12n. Combining like terms, We get 9 plus 12 to be 21n plus 9 over n. And since the degree of the numerator is the same as the degree of the denominator, talking about limits approaching infinity, this is just the ratio between the leading coefficient of the numerator and the leading coefficient of the denominator, which is 21. Whole lot of work to get the same answer we did with just using triangles and rectangles. Now, you might ask, well, what's the point? There's got to be an easier way to do this. Well, there is an easier way to do this, and we will go over that very soon. But what you need to know now is this process is something that never goes away. And finding the limit as a piece, the number of pieces of something approaches infinity of the sum of those things, is used absolutely everywhere in physics and chemistry and biology, and I'm using it right now in vector calculus. It just doesn't go away. This is the rule that if you have something like this, that means that you can use what we call definite integrals, and we'll go over that in a second. So let's do another one, maybe a little bit harder. Let's say our function is something simple. Maybe, let's say x minus 1 squared. X plus 1 squared. So we have this parabola, but it's on the x-axis. And let's say we want to find the area under this parabola between 1 and 3. So first we have to find our delta x and our x sub I. Well, delta x is going to be the ending point minus the starting point divided by n, which is 2 over n. And our delta, or our x sub I, is going to be, remember, our delta x times I. So it's just 2i over n. So now we can start the whole limit summation process. And we'll take the limit as n approaches infinity of the sum from I equals 1 to n. Remember, we're taking the height times the width, which is going to be, that should just be a regular arrow, not equals. The limit of the sum n. So we're putting our x sub I into the function, which gives us 2i over n plus 1 squared. 2i over n plus 1 squared times our delta x, which is 2 over n. And this is something that we can solve. So first thing, we want to simplify the summation, because that's really, that's ugly. We can make it prettier. So I equals 1 to n. First, we need to square the binomial. So we have expand this binomial, and we will get 4i squared over n squared plus 4i over n plus 1, with the square square multiplied double. And this all gets multiplied by 2 over n. So we can do that part also. The limit as n approaches infinity from I equals 1 to n of, oh man, so this will be 8i squared over n cubed plus 8i over n squared plus 2 over n. And now we can say that this 8 over n cubed is a constant, this 8 over n squared is a constant, and this 2 over n is also a constant. So now we start taking some limits, or some summations, using the formulas we learned. So this is the limit as n approaches infinity of the sum of the first one is going to be 8 over n cubed. The sum of squares we found to be n times n plus 1 times 2n plus 1 all over 6. And then, let me move that a parenthesis. plus 8 over n squared. The sum of just i's is the n times n plus 1 over 2. I'm running out of room, but that's okay because we're almost done. This will be 2 over n times n because it is a constant. That is the rule for the sum of constants. Okay, so now let's see how we can simplify this. First of all, this n will cancel with one of these, and this n will cancel with one of those, and these n's will cancel. So now we're left with the limit as n approaches infinity of 8 times n plus 1 times 2n plus 1 over 6n squared plus 8n plus 1 over 2n plus 2. We're taking the limit of all of that. And so now we need the limit as n approaches infinity. Should we put this all together? No, I don't want to. So we're going to take the limits of each of these pieces separately. So first of all, this first term right here, the degree of the numerator is going to be 2, and the degree of the denominator is 2. So again, since they have equal degrees, we take the leading coefficient of the numerator divided by the leading coefficient of the denominator. Now, when we get the first term of the numerator, it's going to be this 8 times this n times this 2n. So our first term is going to be 16n squared. So the leading coefficient is going to be 16. 19, 16. And the leading coefficient of the denominator is 6. Now for the second part, our leading coefficient will be 8 for the numerator and 2 for the denominator. So that's a 4. And our last, the limit as n approaches infinity of 2 is just going to be 2. Fantastic. So changing these all, we can reduce this to 8/3. 4 we can make 12/3. And 2 we can make 6/3. So we're left with 8 plus 12 is 20, plus 6 is 26/3. Okay, that is now the area under the curve. Now, there is an easier way, and I'm going to show that to you, because this is merely, the reason we're doing all this is to show you where the idea for definite integrals comes from. So we're still dealing with f of x equals x plus 1 squared. First thing I want to do is expand this. So this is going to be x squared plus 2x plus 1. Now we want a definite integral. So we've talked about integrals already. They're very easy. We want to take the integral of x squared plus 2x plus 1 with respect to x, so we throw a dx on the end. And we still want to look at the area from 1 to 3. So we're going to notate that by putting a little 1 at the bottom and a 3 at the top. So this is actually read the integral of x squared plus 2x plus 1 dx from 1 to 3, or the integral from 1 to 3 of x squared plus 2x plus 1. And now we just integrate. Let that sink in for a second. Kind of put all that idea together in one thought. But don't worry about the 1 to 3 for now, because the first step is just to integrate. And hopefully it's been a while since we've done this. First thing we want to do is rise and divide. So if we integrate the first term, x squared, we rise it to x cubed and divide by 3, because that's our new exponent. Our 2x, we are going to rise to 2x squared and divide by 2. I'll write that out, 2x squared divided by 2. Those 2's are going to cancel out. That's convenient. And then we have a 1, and hopefully you remember when we integrate a constant, you just throw the variable on the end. So that is the integral. I did not forget the plus c, because this is a definite integral, meaning we're definitely going from 1 to 3. So as far as definite integrals go, there is no plus c on the end. There still is a plus c if we were doing an indefinite integral, or just regular integration. So since it's definite, we're not worrying about that. Now, So let's rewrite this to make it pretty and everything. So we're going x cubed over 3 plus x squared plus x from 1 to 3. Now to solve definite integrals, what we're going to do is put the upper bound in first and then subtract it, or subtract from that the lower bound put in. So this is going to become 3 cubed over 3 plus 3 squared plus 3 minus 1 cubed over 3 plus 1 squared plus 1. And this is fairly simple math. This is going to be 9 plus 9 plus 3 minus 1/3 minus 1 minus 1. Okay, so this is minus 2, so if we take that away from the 3, it just becomes a 1, which gives us 19 minus 1/3. 19 times 3 is 57, so we have 57 thirds minus 1/3. I hope this is right. Is this the same thing I got before? 26 thirds? That is not the same thing as I got before. So this should be 56 thirds, so something went wrong. Hold that thought. Figured out what I did, because our x sub I is not just 2i over n. In fact, it is 1 plus 2i over n. It is 1 plus 2i over n because, remember what I didn't, a plus 2i over n. It's a plus I delta x. So a plus I delta x. And I forgot to put in starting point, so that's going to change a whole lot of stuff. For 1, this is going to now be a 2, which makes, this is a 4, this is an 8, which makes this an 8, and this is 16. And this is 16. This is an 8. And this is just 8. This is 16. Nope, that's just 8 also. And so we now have 8 thirds. When we take the limit, I still like 8 thirds. This is now 24 thirds. And this is now an 8, also convenient. So this is also 24 thirds. And 24 plus 24 is 48 plus 8 is, I want to make sure I get that right, 56 thirds. Aha! Now they're the same answer. Congratulations to us. Okay, so here's the limit method. Gives us this answer. And that's the very strict definition of the definite integral. But utilizing the definite integral, we have all that fun stuff, which just gives us this. And also, if you're using the definite integral, there's a lot less ways that you can mess up. Every time I do the definite integral, I get the right answer. When we use the limit definition, when I use the limit definition, messes up a lot. Anyway, in your book, I want you to do numbers on page 269, numbers 47 through 56. You can use the definite integral or the limit. I would like you to try the limit method on some of them, but it's very easy to check your answer using the definite integrals. These are all polynomial functions, so there's nothing weird going on. Just remember, if you're using the limit method, pay attention to your starting point, which I did not do last time. All right. Good luck. You can ask me questions tomorrow.